Hello, physics students. We are just getting out of our Christmas break. I hope you had a great Christmas and happy beginning to the new year. There's a lot of craziness in this world, but tell you what, physics is one of the good things about the world, along with math and along with some other things that I won't say on this video. But just want to review a couple of things as we get back into it. Remember that the name of our class is calculus-based physics, particularly mechanics. So we're looking at mechanics. All right, mechanics is kind of all about motion and forces and things like that with objects. The first thing we did with mechanics is a subtopic called kinematics. Pardon my bad handwriting. Kinematics. Kinematics is kind of as regards the how objects move, the how of motion. And now we're getting more into something called dynamics, which is the why objects move. So when we get into dynamics, we're getting much more into Newton's laws. So let's just take a good look at Newton's laws. What laws of physics govern motion? Newton's first law: an object will remain at rest, or will continue to move with constant velocity, and I would add, in a straight line. In a straight line. If and only if the net force, meaning all the sum of all the forces, equals 0. So there could be a force on an object, and if there was another force that counteracted that force, then it would still be in mechanical equilibrium. It would still continue to be at rest or continue to move with constant velocity in a straight line, because the net force, the overall force, would be 0. And that's called mechanical equilibrium. We might call this first law, there's one word that kind of summarizes that law, and it is inertia. An object wants to keep doing what it's been doing, and the only thing that changes that is an outside force, something outside of that object or system. A lot of times I like to think about that with the universe. In order for the universe to be or to do anything, there has to be something outside of the universe. For there to be motion within the system of the universe, that motion had to be caused by something outside of the universe, something other than the universe itself. And that gets into a much bigger, deeper question that I think is the most important question of all, and I'll probably just leave it there for now. But a lot of times we get into the bigger question has to follow from a lot of things we see in physics. All right, Newton's second law. Newton's second law is F equals ma, or more precisely, the net force on an object equals the mass of that object times the acceleration of that object. So the net force on an object by anything outside of that object itself. In other words, there's something else, other things that are acting on that object, and they provide some sort of an overall net sum force. That value of the net force will equal the mass of the object times the acceleration of the object. Notice these vector symbols. Force is a vector, acceleration is a vector, mass is a scalar. So mass is just a magnitude quantity. It doesn't have a direction, but force and acceleration do. So you can break the force down, you can break the acceleration down into its vector components, like in the x direction or the y direction or the z direction, or things like that. Newton's third law is, we hadn't gotten into this yet. We'll get more into this, I think, in chapter 7. It's that every action has an equal and opposite reaction. For every action, there's an equal and opposite reaction. But more precisely, it's this equation. The force of object A on object B is equal to the negative or the opposite of the magnitude of the force of object B back on object A. In other words, when you push on a wall with 50 newtons of force, the wall pushes back on you with the same magnitude of the force, but in the opposite direction, so that it has the different sign. So negative, if you call the direction of your force positive, then your force would be positive 50 newtons. And so then the wall's force back on you would then be defined as negative 50 newtons because it's pushing in the opposite direction. All right, so that gets us back into kind of what we were just delving into as we finished up chapter 5 before Christmas break.
All right, so chapter 6, looking at the e-text for your book, your textbook, is about dynamics, motion along a line. So we're just going to look kind of at one-dimensional motion as regards how force makes that happen. So you can see maybe this airplane picture is a good thought-provoking picture of that. The airplane, the jet engines of that airplane are all pushing backwards on the air, which means the air is also pushing forward on them, which is what is causing the plane to accelerate down the runway in a straight line. Now, the plane kind of has, because of the wings and because of lift on the wings, which is an interesting concept I'd like to tell you about sometime, but not right now. The plane is actually going in 2 dimensions. It's going horizontally down the runway, but it's also going vertically up as well. So, how are Newton's laws used to solve problems? Newton's first and second laws are vector quantities. To use them, what you do is this. These are 3 really good steps. Number 1, draw a free body diagram. So when we draw a free body diagram, all right, by way of reminder, here's another reminder about what a free body diagram is. A free body diagram is making a simplification. It's drawing a dot. Okay, a dot represents an object. Then you're going to draw the forces on that object. So let's say this object represents let's say a box sitting on the ground, and someone is pulling a rope attached to that box. Okay. Sorry about I'm not trying to really draw this very well, but anyway, they're pulling that box this way. So we would say, what forces are acting on that box? Well, gravity. And so we represent gravity is pulling down on the box. We draw a line, it's kind of like a vector that starts at the dot and points in the direction of that force. So this would be like the gravitational force. I'm just going to do F with a little G subscript, the force of gravity. Sometimes you could do like a big G to represent that or something. There's different ways you can do it. What's another force? Another force is the what's called the normal force. The normal force, F sub n, or you might put N for normal force, is the force of the ground on that box. And the normal force and the gravitational force are going to equal each other in this case, but because I know that the box is not moving down. It's not accelerating upward or accelerating downward vertically, so they have to cancel each other out. What other forces happening on that box? The pull force of the rope. All right. So we might say this is a tension force. You might put a T or a little t or an F with a little T on there for tension. There's different letters you can use. What else is happening? There might be friction. If the box is moving, or even if it's not moving, the friction is always going to oppose the direction that the direction of movement, or the direction that the movement would be in. So if the movement would be to the right, or if it is to the right, or if it would be to the right, then the friction force is going to be opposite of that. So this is the friction force. Usually we use a little F, or you might use an F with a subscript F, like that, either way. And so then it's like you're just letting, once you get the free body diagram, you let that free body diagram speak to you. What we read here in this direction is it says, read the X and Y components of the forces directly off the free body diagram. The sum of the forces in the X direction equals the mass times the acceleration in the X direction. And the sum of the forces in the Y direction equals the mass times the acceleration in the Y direction. Now the mass doesn't change. The mass is the mass of that object. And it's going to be the same in both of these equations, whatever the mass of that object is. The acceleration in the X direction, the acceleration in the Y direction, they are independent of one another. Alright, so anyway, I guess I'll go ahead and say this. If you did the sum of the forces in the X direction here, I might not have enough room. Let's say the sum of the forces in the X direction is equal to, and I probably need to have an angle here, okay? Theta is going to equal the tension force times what? Times the cosine of theta. That's this component, the horizontal component of that force. That's using trig. All right. What else is happening in the X direction? Plus the friction force, or we may say minus the friction force, or really it's like plus the friction force times the cosine of that angle. That's 180, which is just a -1. So it's like minus the friction force. I'm kind of going too far into this because you're not quite ready for this yet, probably. But that will equal that's the only forces acting in the horizontal direction. That's the mass times the acceleration in the X direction. And we'd be able to solve an equation and figure something out. Do the same thing in the Y direction. Sum of the forces in the Y direction is equal to, we have the normal force minus the gravitational force, or we might say the normal force times the sine of 90 degrees, which is just +1, plus gravitational force times the sine of 270, because that's the angle it's acting at, and that's just -1, plus the tension, or the force of tension here, times the sine of theta, whatever that theta is, and that's equal to the mass times the acceleration in the Y direction. And we could solve that as well. Yeah, so that's kind of how it works. How are dynamics problems solved? A net force on an object causes the object to accelerate. Identify the forces and draw a free body diagram. That's what we just showed how to do. Use Newton's second law. What is the second law? F equals ma, which is what we already showed as well, to find the object's acceleration. So we use those equations I kind of just wrote. You can use that to solve for the acceleration of that object in the X or Y direction. And once you do that, then you have enough information to then go back to what we've learned before, kinematics. Those kinematics equations. Once we have acceleration, right? Once we have acceleration, then we can do what? The antiderivative to get velocity, and the antiderivative of that to get position, and so on and so forth. How are equilibrium problems solved? An object at rest or moving with constant velocity is in equilibrium with no net force. Identify the forces and draw a free body diagram. That's what we've already said. use Newton's second law again, which is, again, what we've already said. But if it's in equilibrium, we know that the acceleration is 0. So if it's not accelerating, you just put in 0 for the acceleration, and you can solve for whatever is unknown about that problem. This is called statics. So we have dynamics and statics. Dynamics is when an object is moving, when it has a net force that is not equal to 0, and it has an acceleration. Statics is like when you're solving a problem where the object is not moving, when it does not have an acceleration. It has forces, but those forces are causing the object to be in equilibrium, and so the object is not accelerating. Statics is something like, a bridge or a skyscraper. Those should be statics problems because you're hoping, you're designing it so that it won't move, so that it won't have any acceleration. Dynamics would be something more like an airplane or a car or a golf ball or something like that, where an object is accelerating. We're going to go through some of the lecture slides now for Chapter 6. Reading questions. Newton's first law can be applied to what? Newton's first law, that is, an object at rest stays at rest, and an object in motion stays in motion unless they're acted on by an outside force. Or another way to put that is an object, how does it put it? Let me go back. How does it put it in the book? Let me go back. This is the way the textbook puts it. An object will remain at rest or will continue to move with constant velocity in a straight line when the net force is 0. Okay, so let's see if we can answer the question now. When the net force is 0. That applies to static equilibrium, which is what I talked about before. That's when an object is not moving and has no acceleration. And dynamic equilibrium, that's actually also when an object has no acceleration, but it may be moving with a constant velocity. Kind of like a planet that's orbiting around the sun or something. Or maybe that might not be the best example because you do have the force of gravity of the sun, which is making the planet revolve around it. So it is accelerating around it because its velocity is changing direction. Not changing magnitude, but changing direction. That's not the best example. So if you have a car going down the road at a constant velocity, that's dynamic equilibrium. Static equilibrium would be when a car is just sitting there in the driveway. Inertial equilibrium is not really a thing. That's not a term that we have in physics. So I believe it's A and C. So I think the answer choice is choice E. What is mass? Is mass a force or a measurement or an intrinsic property? Mass is an intrinsic property of matter. It's not a force. It's really, you can measure mass, but the measurement of mass is not mass itself. Mass itself is an intrinsic property. It is something that is tied to the nature of the whatever object, whatever material we're talking about. All right. Weight is the force that is connected to mass. Or we say the force of gravity is connected to mass. Weight is actually the measurement of that force of gravity on a scale. So gravity is what? So mass is an intrinsic property of matter. Gravity is the force due to that mass. Due to that mass, you have a force, and that force is called gravity. Weight is the measurement of that force that is called gravity, which is due to the mass, which is the intrinsic property of matter. So it's kind of, the book is trying to get us to distinguish those concepts in our mind. So go back and think about what those mean again. Mass is an inherent property of matter. Gravity is a force that happens because of the mass. And weight is a measurement of that force with some sort of measuring device. All right, the coefficient of static friction is always going to be larger than the coefficient of kinetic friction. Remember that static friction is when you're pulling on something, but it's not moving. Once you break the molecular bonds, and there's always going to be some sort of a molecular bond when something is sitting on something else or connected to something else or touching something else. Once those initial molecular bonds are broken, you still have friction, but it's not the same kind of friction. It's called kinetic friction when something is already moving. That's kinetic friction, and it's never as much as the initial static friction. So you might pull on, once you get something moving due to friction, it's harder to get it to started moving than it is to keep it moving because kinetic friction is always a little less than static friction. All right. The force of friction is described by, we haven't talked about this. I believe it's going to be choice C, a model of friction. We'll talk about that later. When an object moves through the air, the magnitude of the drag force on it the drag force is going to increase as the speed of the object increases, because as the speed of the object increases, the more air it encounters, the rate of the air that it encounters is going to increase, which is what makes the drag force happen in the first place. Terminal speed, let's see, it's not the minimum speed an object needs to, nope, that's not it. The speed at which the drag force cancels the gravitational force, that is correct. So terminal velocity or terminal speed is like when, if you jump out of an airplane, parachute out of an airplane or something, after a little while, you could reach what's called terminal speed, and you would no longer be accelerating downward. That's when you feel weightless and you feel like you're flying. It's when when your velocity reaches a certain point, the drag force is increasing and increasing until the velocity reaches a certain point where the drag force then is equal to the gravitational force, and therefore there is no longer a net force on you, and you're not accelerating because the drag and gravity cancel each other out. All right. The equilibrium model. In the absence of a net force, an object is at rest or moves with constant velocity. Its acceleration is zero, and we say that it is in equilibrium. So that bridge, we would hope, would be in equilibrium, static equilibrium, actually. The concept of equilibrium is essential for the engineering analysis of stationary objects such as bridges. When the acceleration is zero, then Newton's second law in two dimensions becomes the net force equals ma, but since a is zero, then the ma is going to be zero. So the net force equals zero in the x direction or the y direction. Mechanical equilibrium. For objects on which the net force is zero, model the object as a particle with no acceleration. A particle is at rest. At rest is in equilibrium. Particle moving in a straight line at constant speed is also in equilibrium. So the particle at rest is called static equilibrium. The particle moving in a straight line at constant velocity is called dynamic equilibrium. Either way, A is zero, and this would apply to it. The net force would equal zero. The forces are read, quote unquote, like that from the free body diagram. I would say you're letting the free body diagram speak and communicate. You're talking to the dots. The model fails if the forces don't cancel each other out. That is to say, it's not going to be mechanical equilibrium. It's not going to equal zero. It doesn't fail as far as it will equal ma. It doesn't fail in that way. It just fails to equal zero. Quick check 6.1. This is something we've encountered multiple times already. You have this puck sliding around, going around in a circle because of the string. But if the string breaks at this instant, which way will the puck go? Well, at that point, there's no longer a force pulling the object toward the center. We might even say there's no longer a net force on the object. Therefore, the object will either just stay still or it will travel in a straight line. And since it was already moving, at that instant, it will continue along in a straight line. So the answer would be C, which is Newton's first law. A ring, quick check 6.2. A ring seen from above is pulled by three forces. The ring is not moving. How big is force F? So we have these two forces, and it tells us that the ring is not moving, so force F would have to counteract these two forces. Sorry, don't know why I did that. Oh gosh. Okay, trying to get where I could write on this thing. All right, maybe you would recognize, okay, these two forces are not acting in the x or the y direction. They're acting at an angle, which gives them an x component and a y component. They have an x component and a y component. Okay, so because the angle is theta with the horizontal on both of these things, we could say, what is this component of the force? It would be 10 cosine theta, and this would also be 10 cosine theta, so that these two actually cancel each other out. This one's pulling to the left with 10 cosine theta, this is pulling to the right with 10 cosine theta, and so they cancel each other out. Another way you could think of it is, let's say, the sum of the forces in the x direction are equal to 10. And if we think of it as a standard angle, that's going to be cosine theta. This standard angle would be plus 10 cosine of 180 minus theta equals 0. And our trig properties would tell us that cosine of 180 minus theta is the same thing as negative cosine theta. So it becomes 10 cosine theta minus 10 cosine theta. And they would cancel each other out, and so you get 0 equals 0. So anyway, those things cancel each other out. But in the vertical direction, they don't cancel each other out. In fact, they add to one another. This one's pulling up. This one's also pulling up. So we got the sum of the forces in the y direction would be 10 sine theta plus 10 sine of 180 minus theta plus f sine, and this is f, okay, plus f, what's this angle? What's this standard angle? Sine of 270. And that equals 0. Because how do I know it equals 0? Because it says the ring is not moving. So, trig properties would tell us that sine of 180 minus theta is the exact same thing as sine of theta. So 10 sine theta plus 10 sine theta. What's sine of 270? It's negative 1. So minus f equals 0. So 20 sine theta minus f equals 0. So 20 sine theta equals f. If the ring is not moving, the magnitude of f would have to be 20 sine theta. Okay. And there may be, quicker ways to think about that. I'm just trying to show you a thorough way of figuring these things out that will work in any situation. All right, example 6.2, towing a car up a hill. A car with a weight of 15,000 newtons is being towed up a 20-degree slope at constant velocity. What does constant velocity mean? The wheel should already be turning for you. Constant velocity means what? Acceleration is 0. So it means the sum of the forces is going to equal 0. Friction is negligible. The tow rope is rated at 6,000 newtons maximum tension. Will it break? Okay. Let's do some free body diagramming on this thing. Just draw a picture. I'm just going to say this car. Alright, here's the car. Just going to draw it like that. That's the car. It is being towed up the 20-degree slope. And I'm going to invert. I'm going to slant my X and Y axis so that the X axis is parallel to the incline. It's going up the hill. And the Y axis is perpendicular to the incline. I have the weight of the object acting directly toward the center of the earth. So that's the weight of the object. And the weight is 15,000 newtons. I also have the normal force. The normal force, let's call that little n. That's the force of the ramp itself on the car. So now let me simplify this thing with a dot. Alright, this angle is the same as that angle. That's the 20 degrees. We can talk more about that later. I think I've already shown you that before, but about how you can logically get to that conclusion. So that's 20 degrees. The normal force. And the force of the tow rope. Let's call that tension. So, really the only thing of interest in this problem is the X direction, because that's the direction that the tow rope is pulling in. The Y direction is not going to help us at all with this. So, I could do the Y. The sum of the forces in the Y direction is equal to the normal force times the sine of 90 plus 15,000 sine of, what is that standard angle right there? It's 270 minus 20, so sine of 250. And that will equal 0. Because it's not accelerating in the Y direction. It's not floating up off the ramp. It's not sinking down into the ramp. It is not accelerating in the Y direction. And what I could do is use that to find the normal force, but I'm not being asked anything about the normal force. So I don't have to find the normal force. So that, again, that's not even going to be of interest. Let's do the sum of the forces in the X direction. And notice that it said friction is negligible. Otherwise, we would have done a friction force that way, right? But since friction force is negligible, we're not going to do that. So what do we have in the X direction? We have the tension times the cosine of 0, because that standard angle is 0. And I didn't mean to say theta, I meant to say 0. And what is cosine of 0? It's just 1. So You don't really have to do cosine 0. I'm just trying to do this in a very thorough way that works all the time. And you can do that by, if you always do standard angles, then when you do in the y direction, you can always do the sine of the standard angle. When you do the x direction, you can always do the cosine of the standard angle. And that will always take care of your sines, your SIGNs for you. It'll take care of the pluses and minuses. You just say plus every time. And as long as you do the standard angle, you're going to get the right sines to come out of that. So plus 15,000 times cosine of that standard angle, which is 250. Notice we can also say it's the normal force, but the normal force is not giving any components to the x direction. It's completely in the y direction. But if you wanted to, you could say plus the normal force cosine of 90, but cosine of 90 is 0, which would make that become 0 anyway, which ties into what we've said, that it doesn't have any effect in the x direction. So I'm not going to put it. And that's going to equal 0. How do I know it equals 0? Because it says at a constant velocity. It really equals what? It really equals ma. But since it's a constant velocity, a is 0, which makes this whole thing be 0. So equals 0. And I have everything I need except the tension force. And the tension force is what I'm going to solve for to be able to answer the question. So cosine of 0 is just 1. So this is just going to be tension. And cosine of 15,000 times cosine of 250 is what? Let's calculate that. Make sure your calculator is in what mode? Degree mode, because we're talking about 250 degrees. 15,000 times cosine of 250. I get negative 5,130. So minus 5,130 equals 0. Move the 5,130 over. T equals 5,130 newtons. So the question says the tow rope is rated at 6,000 newtons of maximum tension. Will it break? Well, since we just determined that that the tension in the rope is 5,130 newtons, it will not break because it can do up to 6,000. So the answer is no. All right. This is how the book does it. They do it just like we do it, I think, pretty much. They said 5,100, we said 5,130. They're just doing, they said 5,100 because they're doing the correct amount of significant digits. Since it's 15,000 newtons, that's only 2 significant digits, so they just said 5,100 instead of 5,130. So they did the same thing we did. They got pretty much the same thing we got. So yeah. Quick check 6.3. A car is parked on a hill. Which is the correct free body diagram? All right, maybe pause it and decide before we talk about it. All right, what do we got? We got it's parked on a hill. So there has to be friction for it to remain parked and not just slide down. So we're going to assume that there is friction. So there's going to be gravity. Which way does gravity go? It goes straight toward the center of the earth, straight down. There's going to be, the car wants to slide down the hill, right? But friction is going to oppose that motion that wants to happen. So friction is going to point in the opposite direction. It's going to point up the hill. So it's going to have a friction force there. And it's also going to have a normal force here. So I think choice C is going to be the right one. The car is towed to the right at constant speed, which is the correct free body diagram. All right, we got gravity, we got normal force, and notice those two arrows need to be the same length because it's not flying up in the air or sinking into the ground. So the vertical forces must cancel each other out. The tow rope has a force, and there's also a friction force. So C, D, and E all have the right arrows, but which one is correct? And how do we know? The length of the arrows. Should the tow rope's arrow force or the friction arrow force be longer, or should they be the same? How do we know? It says at constant speed, which means the acceleration is 0, which means the forces in the horizontal direction need to cancel each other out in order for that to be the case. So D, where they're the same length, has to be correct. Newton's second law, using it. The essence of Newtonian mechanics can be expressed in 2 steps. The forces on an object determine its acceleration. So F equals ma, or which can be rearranged to say A equals F over m. The object's trajectory can be determined by using A in the equations of kinematics. So once you figure out the acceleration, then you can get the velocity or position or whatever using the kinematic stuff we've talked about in the first several chapters. If you want to go back and read these, pause it and read these if you want to. Quick check 6.5. The cart is initially at rest. Force F is applied to the cart for time delta t, after which the car has speed v. Suppose the same force is applied for the same time to a second cart with twice the mass. Friction is negligible. Afterward, the second cart's speed will be what? Alright, let's see here. Trying to get out. There we go. Alright. Well, what do we know? F equals ma, right? The force is the same. Alright. If the mass is doubled, if that force is going to remain the same, then the acceleration has to be cut in half in order for it to keep that the same, right? So we might even work it out like this if we wanted to be real thorough about it. Here, A will equal F over m. But if the mass was doubled, then A would equal F over 2m, which could be written as 1/2 F over m. So this compared to this is the acceleration is cut in half. So if the acceleration is cut in half, then the velocity would end up being half of what it would have been. Right? Velocity is just a linear relationship to acceleration. So it should be B. And it is. Example 6.3. Speed of a towed car. A 15,000 kilogram car is pulled by a tow truck. The tension in the tow rope is 2,500 newtons, and a 200 newton friction force opposes the motion. If the car starts from rest, what is its speed after 5 seconds? Okay, let's draw a free body diagram. I think I could just go straight to the dot here. We have gravity. What is gravity? Gravity, or weight, or whatever, the force of gravity. I'm just going to put that as a big G. How about that? The force of gravity is equal to 1,500 kilograms times 9.8. That's gravity, the gravitational force. I also have what? I have a normal force, which is going to equal that same thing. It's going to also equal, it's got to equal gravity. Otherwise, our car would be accelerating up into the air or accelerating down into the ground, and we know that's not happening. It's being pulled by a tow truck. The tension in the tow rope is 2,500 newtons. 2,500 newtons. And the friction force, notice my friction force arrow is not as long as my tension arrow, is only 200 newtons. All right, again, if I do my sum of the forces, the y direction here is not going to be of interest to us because it's not accelerating up or down, but it is accelerating horizontally. So I'm just going to go straight to the sum of the forces in the x direction. What are they going to be? They're going to be 2,500 Let me take this down here where I have more room. Sum of the forces in the x direction are equal to 2,500. And if I want to be thorough, I would say cosine of 0, but that's just going to be 1. Plus 200 cosine of 180, but that's just going to be negative 1. And that's going to equal MA. And the mass, that's equal to MA. Where the mass, I'm just going to go ahead and put the mass, where the mass is 1,500 kilograms times the acceleration in the x direction. Now that's just going to be 2,500 minus 200 equals 1,500 A. So what is that? 2,300 equals 1,500 A. So then if I divide, then I'll have my acceleration. 2,300 divided by 1,500 is 1.53. So 1.53. I may should just say 2 because the significant digits here, the limiting one would be there's only one significant digit there. But anyway, we'll just go with 1.53 to be more exact for a little while. So it's got this acceleration for 5 seconds. So let's go A. We're now doing kinematics, right? A equals 1.53. So, and I'm doing it into the horizontal direction. So VF x is going to equal the antiderivative of that with respect to time, 1.53 t plus VI x, which is just 0. And I already know that I can find the answer that it's looking for now. So VF x is what I'm looking for. It's 1.53 times the time which is given to me right here, 5 seconds. Do that multiplication. I get 7.6 repeating. So VF of x is equal to 7.67 meters per second. That should be the answer. That's the car's speed after 5 seconds undergoing that acceleration. Okay, this is what the book does. You might want to look at all that. They do, they draw the car, they draw even a motion diagram with these increasing arrows, and then they do their free body diagram and all that. But you may be able to skip some of these steps and go straight to a more direct line to the answer. But this is a very thorough way to handle it, obviously. Okay. This is their sum of the forces in the x, sum of the forces in the y, and so on. You could read that if you want. They get 1.53 for the acceleration. then once they do that, they do what we said here. And they get 7.7, which is what we said as well for the speed. Okay. Quick check 6.6. The box is sitting on the floor of an elevator. The elevator is accelerating upward. The magnitude of the normal force on the box is what compared to gravity, or compared to mg? Let's look. You may already know the answer to this just from kind of a intuition. All right. If it's accelerating upward, that means that my normal force has to be larger than my gravitational force, which is mg. So N is greater than mg if this elevator is accelerating upward. If the box, which means the box is also accelerating upward. All right. You can read that if you would like. Mass and intrinsic property. I'm going to stop it right here because this is getting into a little bit different material. May go ahead and do another video for another, but this is a long enough video for now.